Hi, this is Arpan Gupta. Today I will discuss about convolution neural network with TensorFlow. And I assume that you must be knowing about the MNIST dataset and you know how to perform convolution neural network basics. So first of all, for the TensorFlow, we would require the dataset which is already in the TensorFlow, and we will import that dataset, and the code will be very simple and straightforward, which requires writing some functions, which is like writing about the model architecture, and you would like to write the weights and the biases in TensorFlow. So it will be very simple, and let's see how we will perform this convolution neural network with a basic MNIST dataset in so let's first import this libraries and like NumPy, Matplotlib, TensorFlow, and from the TensorFlow and dot examples tutorials MNIST, you import the input data where you do not need to download from anywhere. And after importing these libraries, you can just read the data, load the data from this directory, and you will write one hot is equal to true because you would like to have the labels in one hot encoded format. So as we know that MNIST is the image data where we have the images in the form of pixels, which is 28 by 28 size pixels, and each of these images belongs to one of these labels, which is 0 to 9. So we have which is a multi classification problem, so we have 0 to 9 labels. So after we have loaded this data in which is in the df, now we know that there are 28 by 28 pixel size images. So 28 by 28 makes it 784. So the number of inputs which we fed into this network will be 784, which is the starting point of this convolution neural network. And the number of classes, which is the final output, is 10 because we have 10 labels. So these two important things, because 28 by 28 is equal to 784, and dropout is being used for removing some of the connections randomly in the while the model is being trained. And this is just like a type of regularization to avoid overfitting. So in the TensorFlow, we need to first, you can say we need to first encode in such format like that the X and Y. So we have the data, and we should have the data in the format of X. We will write it as tf dot placeholder, and the placeholder will be the float type, and the shape should be the none and number of inputs, which is a two-dimensional matrix. So we are writing none, and instead of none we can write -1, and none means that we don't want to specify the number of rows ahead of time. So we might require to change it during the model training. So we are just specifying the number of rows as none and the number of columns as number of inputs. So as we see that if we squeeze the one image which is 28 by 28, if you squeeze it and make it a straight line, it will become 28 by 28, which will be equal to 784. So you can say that we have rows equal to the number of images in the data, and we have columns which is equal to the 28 by 28, which is 784. So from the network will try to convert these X and try to correlate with this Y, and Y which is equal to where we have the shape as the same none and the number of classes is 10. So as we have already taken as one hot encoded, so it will be something like the number of observations, which is the number of rows, and the number of columns will be equal to number of classes. So it is something like this, which is will be like 0 and 101 type. Now we will encode for keep prob, which is again a tf dot placeholder, and we have tf dot float 32. So tf dot float 32 is telling that all the numbers which is inside this matrix should be of the format of float 32. Now Now what we are doing is we are taking the neural network training parameters, and as we know that there are a number of images. So say we have for an example, say we have 100 images. So how many images at a time you need to train, that is the batch size. So we are taking here 200. So batch size will be this number of images will go into the network at a time and go forward in the network and back propagate, and then again 200 new images will be going into the network and retrain and go back propagate. So similar to the this, and the number of steps is which I will explain you later, which is, and the learning rate is similar to like eta, which is how fast the model will train, network will be trained. And display step is like after how many steps you want to show, that I will tell you. The number of steps and display step is, which is we will understand here something where we will write the session. So now after defining these things, you would write you would define two functions, which is convolution image, and the next is max pooling. So we already know that what is convolution, and convolution we would require the weight matrix, and we already have the x, which is the input data, and we would convolve it using the weight matrix, which is w, and then add the biases, which is b, and the strides is like how this filter maps, which is the filter map in the convolution, uh, at each step how many steps will it move forward. So if a stride is 1, so that means the filter map will move by 1 pixel. Now we will convert this x, and we will see that how the initial x is convolved with w. So we are writing tf.nn, which is neural network dot conv 2d. So we are using the function conv 2d inside the TensorFlow, which is inside the submodule of nn. We are feeding x, we are feeding w, which is the weight matrix. We will tell what is the weight matrix. It is a dictionary which is mentioned here. So after this x, w, now the strides, we need to give the strides. We are giving in a 4-dimensional matrix. So first is 1 and strides, comma 1. So strides, comma strides, that means it will move along the image in x and y direction by an amount of 1 unit. So if you choose the strides as 2, so it will move by 2 pixels. Now padding is equal to same, that means we are padding at the edges and the corners, and we are giving the padding as same. Now after this x is converted and it is convolved with w with the strides and padding, it is again converted into x. We just converted x into x, and then we are adding the bias, which is b. So after this convolution we are adding bias, which is b, to x. So we are writing tf.nn.bias add x comma b. So it is now x has been converted into x by using the conv2d function, and then it is again converted into x by using the bias add function. So now final output is tf.nn.relu, which is an activation function, and this activation function is basically used to add some kind of non-linearities in the network. So we have other kind of functions like tanh, sigmoid, and similar to that it is a ReLU activation function, which tries to incorporate some kind of non-linearities. So model learns the non-linearities in the data. So we are just convolving image. So first we used conv2d function, then bias add function, and then the ReLU function. So x being converted into x, then addition of bias and converted into x again, and then x is activated by using this function ReLU. So after this function is going to return this convolved image, bias addition, and this ReLU activation function. So the next function is the max pooling layer, which is we know that max pooling, we are given the image, and we are given the filter size. So filter size will be something like k by k. It will be k by k, and we have 4 dimensions, so we are putting 1 and 1 here. So here we have the grayscale image. That's why we don't have the number channels. So the channels is only one. So the number of pixels is like 28 by 28, and it is only one. Had it been red, green, and blue, so we then have the number of channels as 3. But in this case, we have the number of channels as 1. So that's why we have 1 here. And so we are giving a k is equal to 3, and we are again using the submodule function, which is tf.nn.maxpool, and we are giving the x, which is the output, which will be the output of this the same x which we are having here, but we are just giving a generalized x, and then we are giving the size of filter of max pool during the max pooling, and we are giving the strides, just similar to how this filter will move during the max pooling in this, and the padding is given the same. So these two are the functions which will be used during the network architecture building, which is convolution and the max pooling. So now since we already have x, we don't know what is w and what is p. So initially we want to initialize with some random values, and so after we fed it into the network, the model will learn what are the best weights and biases after the optimization of the cost function. So first let's initialize this weight matrix, which will be a dictionary of we have 4 layers here hidden. So first for the first one we are having w1, w2, w3, w4. So each of these are the matrices, and we will be encoded into the TensorFlow variable. So tf.variable, we already know the values. So we are random normal distribution. We are choosing tf.random normal for creating this 4-dimensional matrix. So it is saying that 5 by 5 will be the filter size, and then it will output 32 feature maps after the first convolution. And then we have w2, then we have w3, and then we have w4. So first one is being used for creating 32 feature maps after first convolution. Then there is another matrix, which is w2, which is again taking 32 feature maps, and it will convolve and then again create 64 feature maps, and then later on it will be converted. These are, since we are during the convolution, we have 2-dimensional matrices and we have feature maps, several number of feature maps, but later on we convert this 2-dimensional into a just 1-dimensional vector by just multiplying by the number of rows and number of columns in the images. So at the third stage we are converting into dense. That will be, we are creating something around 7,764, and it will be, now it will be dense, and now we have 1024 as the output coming out of this. And then in the last case we have 1024 neurons, and the output will be number of classes, which is 10. Similarly, we have biases. So biases will be added, which is random normally distributed, and it is again encoded with the variable tf.variable and tf.random normal. So we have 32 values, and we are just adding to these during the convolution, which we have fed into this convolution image function. So we know w, we know b, and we know x. We will be feeding this all during the session when the model is being trained. So let's first create the model architecture, how this this convolution neural network will be looking like. So initially what we are doing is we are writing a function which is for the model architecture. Let's name it something like model_con. We are feeding the 2-dimensional matrix, which is x, which we have encoded here, which is the number of rows as none, which will be equal to the number of images we have in the data, and the number of inputs is 784, which is 28 by 28. So it is 2-dimensional matrix right now. But as we see that the weight metrics are being converted into four-dimensional metrics for the ease, because we do not have only one image, one feature maps. We will be having lot of feature maps, so that will require a lot of maps, and those can be incorporated into the four-dimensional metrics. So we are just converting this x into tf dot reshape x, which is initially fed, which is the two-dimensional metrics, and we will convert into a shape which is -1. -1 is written because we don't know the number of images which we will be feeding into the session, but you can say it is the number of rows. It is not equal, but we can say just we don't know, that's why we are just feeding at -1. Now we have the images of the size 28 by 28, that's why it is like this. So, and then we have this one for the number of channels. So this is size of the image 28 by 28, and this is for the number of channels. So here we don't have the colored image, which is red, green and blue channels. So that's why if had it been a red, green, blue channels, we would be putting here as 3, but it is a simple gray image, so it is something like this. So now since we have converted x into a four-dimensional TensorFlow variable, and now what we are going to do is we are going to start the convolution, and we are going to start creating layers of. So first layer is this, second layer convolving and pooling again, then third is fully connected layer, and the final is the output. So what we are doing in the first one is convolution underscore image, which is this function which is used for convolution. What is it requires? It requires the image data, which is we are feeding it. Initially it was two-dimensional, but we reshaped into four-dimensional matrix. We are feeding that. Then we need to give weights and we need to give biases. Since weight is a dictionary of weights in each of these layers. So first one, W1, is for the first layer of the convolution neural network. So we are just accessing this first weight matrix by just putting the key value, which is W1, which is shown here. So we are accessing the W1 of W, so which is the first weight matrix for the first convolution. And then similarly we are accessing the first bias matrix, which is again B1, and we are putting the strides as 1. So after this convolution, we have given the X, we have given W, we have given bias, strides, everything is given. It is converted into it is convolved, and then it returns the C1, which is showing, which is the result of here. Once the C1 is returned, we are doing the max pooling, and we are telling the size of the filter, which is k is equal to 2 by 2 size, and we are again we are doing the max pooling for the same C1, and it is converting into C1. So first convolution and max pooling C1, then second convolution max pooling. For the second convolution, we are putting W2 and B2 because we are accessing the second weight matrix and second bias matrix, something like. So convolution, so first convolution layer, second convolution layer. So it is like first image input data, which is four-dimensional. It was two-dimensional, converted into four-dimensional. Then convolution layer, max pooling layer. This is first layer of each of these, and then second layer of convolution image and the max pooling. And after this, we are just converting this four-dimensional into something like this. So we are reshaping now the C1, and we are converting with this W3. We know that it is two-dimensional matrix W3. So we want to convert into W3 get shape and convert into list and take the 0. So it will give you something 7764. So we want the C1 to be equal to be having the dimension of 7764, so that we can do some kind of matrix multiplication. So once we do this thing, After this layer, we are converting this into C1, which will be of shape of this -1 times -1 comma 7764. And we want to do this because we want to multiply in this third layer, we want to multiply with W3. So we know that number of columns should be equal to the number of rows, and that's the reason we are converting and reshaping this C1 in such a way so that we can multiply with W3. So once it is reshaped, we are just matrix multiplication. So we are using the matmul function tf.matmul, and C1 is matrix multiplied with the third weight matrix of W. And then we are adding the bias to C1, and then we are doing the ReLU activation. Once this is converted, so we can see that this at this point we were having C1 as this, and we had this W3 matrix as this. Once we matrix multiplication, we do the matrix multiplication, we will have we will have the dimension of -1 1024. So once we have these dimensions, we would like to convert into the number of columns as 10, because the final aim is to get reach to the number of columns as 10, because we have 10 labels. So now we are using the dropout just to avoid the regularization. So tf.nn.dropout, which is dropout is given here. We have already given here this. So dropout will be something as which we have already defined, which is 0.6. So we are just removing some of the connections randomly in the convolution neural network, and we are just doing the dropout just to avoid some kind of some overfitting in this network. After this, since we have this kind of dimension of matrix, we want to use the fourth weight matrix, which is 1024 number of classes. So what we are going to do is 1024 number of classes. This is the W4 matrix. And now we should have some C1 as this dimension, which we already have, because ReLU and dropout won't change the dimensions. It will just have the scaling and some transformations in the numbers, but it won't be having any dimensions change of the matrix. So once we multiply these two, we will get the dimension of -1 and number of classes. -1 is number of rows, and the number of classes will be 10. So once we have multiplied C1 with W4 matrix, and then we have added this bias, at last we are going to get the C1, which will be of the dimensions -1 number of class. So this is the architecture, and this architecture we have developed using this two function, convolution image and max pooling layer, and we have started these weights and biases just for initialization purpose. Now, since we have defined everything, we know X, we know W, initial W, and we know B, what we would we already know the architecture. What we would like to do is now how we would optimize the function, what the network architecture function. So what we need to optimize is, we want to optimize like softmax cross entropy with logits. When we have logistic regression, there we optimize like sigmoid. We have sigmoid function there, and so here we have 10 classes. So what we are going to do is, we are using softmax cross entropy with logits, because we will be optimizing for 10 classes. So now let's see what will be the probabilities. So we are getting the C1. Probabilities will be model underscore con, which we are using this function. We are feeding it xwb and dropout as keep prop, which is which is like this value dropout. And now what we are doing is, we are converting, we are using the softmax function, like similar to this, you can say sigmoid function, where we have only 2 classes. So now the predicted values will be again something of the dimension -1 number of classes. So this is props, and predicted is after the softmax normalization, you can say. And the cost function we want to optimize is like reducing reduce underscore mean, which is tf dot reduce underscore mean, and we are optimizing this softmax cross entropy with logits. We are feeding it these probabilities, which is not normalized with softmax function, feeding these probabilities, and we are feeding the labels, actual labels, and using these probabilities and the actual labels, it will try to optimize this softmax cross entropy with logits function. And it will try to optimize using algorithm which is atom optimizer, similar to, you can say, gradient descent or algorithm. So we are defining here an algorithm which is tf.train atom optimizer. We are feeding the learning rate, which is how fast the model should learn. So this is the algorithm which is optim, and this algorithm is trying to optimize, which is optim.minimize. This algorithm will minimize this cost function. So this is the first, this is, you can say, this is the algorithm. You can first, you should write this. So this is the algorithm, and this is the cost function you want to optimize, feeding the probabilities and the labels. And then you are training, which is optimizing, which is like minimizing the cost function, which is this one. Now we get the actual values, which is like tf.argmax y comma 1, which is like, if you have the final output something like this, which is a, say, two-dimensional matrix. So you have the probabilities. So you have first row, you have the probabilities for 10 classes. You want to see which has the highest probability, which of this column has the highest probability for the first row, second row, and third row, like that. So you get to know, say, first row, had it been there only 3 classes, so first row has third label, so you can say the third label has the highest probability. This is just an example. So you get the actual labels, and then you have the predictions, which is tf.argmax, which is predicted, and we are feeding predicted, which is after the softmax normalization of the probabilities. For the cost function, you will not feed the predicted, you will feed the props, which is without normalization, because this softmax cross entropy with logits already have this normalization inside it. So once you have the actual values and you have the predictions, what you do is you want to see at which locations, at which of these indices actuals and predictions are equal. So tf.equal actual comma preds, it will be true false. And then you want to convert into 0 1 type, so tf.cost convert into accuracy and then into the float type. After it is converted into tf this 0 and 1, you calculate the accuracy, which will be like, what is the average value of this accuracy, means you have 10 values and you have some 0 and some 1, so you get the mean of those 0 and 1, so you get the final how many of these are 0 and 1. Here we have 10 classes, so we want to just see that how many of these are correct and how many of these are not correct. So something like this you can just correlate with some binary, but here we have 10 classes, keep in mind. So now what we are using it, we are just finally, this is the final thing which we are going to do, which is just initializing the session. So init is tf.global variables initializer. So it is going to initialize all the variables which we have used in this TensorFlow. So starting the model with tf.session as says, this is just the way of writing the session, says.run init. So we are initializing all these initial variables, tf.global initializer. And for step in range 1 comma number steps plus 1, so this is the number of steps which we have already defined, how many number of times we are going to take the batches. So batch x, batch y, and we are using the df which is this one. We have taken the data. Inside this data we have the train data and the test data. So what we will write, df.train, and we will write the next batch. So next batch, and the batch size is, which we have already taken, is 200. So it will give the next 200 training images, and you are just taking the x and the y in the batch x and batch y. So these are like similar to x, and this is similar to y, which we have been discussing here, like x and y. This is x, this is y, and here also we are just feeding x and y. So x is similar to that. So batch x will take the role of x, and batch y is taking the role of y, which is taken here, labels is equal to y. So now what we are going to do is sys.run, and what we want to optimize is training. Training is here. We want to minimize the cost function, this softmax, by feeding the probabilities and actual values. So we want to calculate this. So we are feeding this sys.run training, and we are feeding the dictionary x belongs to batch x and y is batch y, and key prob is dropout, which we have already defined initially, which is 0.6. And we are saying that if step is display step, we are saying after each 20 steps we are going to show this loss and accuracy. And the loss and accuracy is like sys.run. Again, you just give it the list of cost function and the list accuracy. For the cost function we need props and y we already have, and for the props we need x, w and b, which we already have during the neural network training. Dropout we have. So what we want to feed as dictionary in this is x, we have batch x, y we have batch y, key prob as 1 for the testing data, which is like the batch loss and accuracy. So now what we have just taken first batch, second batch, third batch, and like this we are just going to take the batches and we are just calculating the batch loss and accuracy, and we want to see how the loss is being decreasing and how the accuracy is increasing. We just need to feed the dictionary of x, y and prob. By this we can just calculate the cost function and probabilities and accuracy, because all those are dependent on only batch x and y. So once we have written this way, at the final stage we would just want to see how this model is going to calculate for the test images. So we just calculate the sys.run accuracy and feed the dictionary, and the dictionary will be the same. Now x we are feeding df.test.images instead of df.train.images. This is, we are feeding df.train.next batch. We are here now feeding df.test.images. We are just taking the first 256 images, and we want to see how well this model is performing on the testing data. So if you see that after just 400 steps, the loss is decreased from this value, which is 85,000, to 800. So it has decreased a lot, and the accuracy for the training data is quite a lot. I mean, initially it was just 0.1, and now we have around 0.9, which is like initially. Now we have 93%. Initially it was just 15%, and now we have 93% after this many steps. So you can just try to tune the batch size on the and see that how this can change. But this is just an overview of how you can just try to, and you can choose the dropout parameter as well, how you can perform the, you can also change the architecture of this. You can increase the number of layers, you can increase the number of pooling layers, you can use the dropout, and all these things which you can change to modify and optimize the architecture. So finally the testing accuracy is 0.95, so which is quite good, and this is which I have already run, so you can see, but it might take around 20 to 30 minutes if your RAM is around 8 GB. So I think you have got an idea of how you would perform this convolution neural network with TensorFlow. I hope you have liked. So if you have liked, please do not forget to like and subscribe. So thanks for watching, and if you have any confusion you can just comment it. Thanks for watching. Bye bye.